Hey guys, these are the notes on projectile motion. Alright, so projectiles are objects that are thrown or launched into the air and they're subject to gravity. The path that the projectile makes will be a curve, and that's called a parabola. We have the same variables as we did with horizontal motion. However, we now have them in the horizontal and vertical at the same time. So we are going to add x's and y's to everything. So horizontal is x's, just like on a graph, your x-axis is horizontal, and then y is to everything that's vertical because your y-axis is vertical. All right, so you'll see all of these in the formula. This helps us keep everything organized. I highly encourage you when you're working out these problems, as you'll see me do in the examples later, is creating a table kind of like this to fill in your information. We also have a couple other symbols. We're going to use theta again for angles, and we're going to have initial velocity overall would just be VI, and then sometimes we'll have to break it down to VIX and VIY. All right, these are the same formulas we've been working with. However, I have gone through and added x's and y's to everything. So on your formula sheet, you don't have the x's and y's added, but what you can do is add x's and y's to everything. But you cannot mix your x's and y's. So if you start putting in x's, it has to stay x's through the formula, or it has to stay y's through the formula. So basically, I can't use my initial horizontal velocity with my acceleration in the vertical. All right. So you have to keep things either x's or y's. All right. There will be some details in a second that kind of go with that. So with horizontal direction in the x direction, our moving object does not slow down. We are going to ignore air resistance. And in reality, air's there, it's going to slow down our object, but for our calculations, we are ignoring it. So that means that our acceleration in the horizontal direction is 0. So every problem you work out, this should just be memorized and known, is that your acceleration in the x direction is 0 meters per second squared. This also means that your initial horizontal velocity is the same as your final horizontal velocity. I'm never going to generally ask you to find your final horizontal velocity. You won't see that come up a lot. A lot of times you can just leave it blank in your chart. You're not going to have to fill up your whole chart. However, I do like to ask a question on the test that gets kind of tricky, where I will already give you the horizontal velocity and vertical initial velocity already worked out, and I'll say, okay, how far has this object gone in 5 seconds? All right, at those 5 seconds, what's its horizontal velocity? So it's tricky in the sense that you'll overthink it because your horizontal velocity doesn't change. So if I'm saying it's going 5 meters per second in the beginning, it's going 5 meters per second whatever amount of time later. Like, it's always going to go that horizontally. So don't let me trick you on the test. All right. For vertical, your projectile experiences gravity. So your VIY is not constant, and our acceleration due to gravity is what we've been using of negative 9.8 meters per second squared. That's as long as we're on Earth, and for this test, we will stay on Earth for all of our calculations. All right. With projectile motion, there are 2 types. There is what I call thrown off a cliff, and then there is launched into the air. Just because it's thrown off a cliff doesn't mean it actually has to be on a cliff. Like your lab where the marble rolled off the table, that would fall under this. So the first type of thrown off a cliff means that it's projected initially in the horizontal direction. So like this cannon on a cliff, it is fired horizontally into the air. It's because of gravity that the cannonball is going towards the ground. If gravity didn't exist, it would, like if it was in outer space and it was fired, the ball would just keep going horizontally. But due to gravity, it's that cannonball is pulled to the ground. So that's the first type. In the first type, you don't have to break down your VIX and VIY because your VIY will be 0. And the initial velocity it gives you will be your VIX. The second type of projectile motion is launched into the air or kicked into the air or thrown into the air at some angle. And when we eventually launch our rockets, this is where we're getting at projectile motion of this type. So like this example has a football player kicking it at some angle up into the air. Notice that at some point it's going to reach its highest point. You'll be having to calculate that. You'll have to calculate how far it goes, the time that it goes, and everything. So let's work out some examples. The first one is type 1. We've got a cannonball launched horizontally from the top of a 25-meter cliff. The ball lands 40 meters away from the cliff, and we want to know the initial velocity of the ball. All right, and I actually don't think I worked out all of this through this example. Let me change that question because I only worked it out to find the distance it goes. So what we're going to do is find, or when you're working these out, set up a table like this. The order of the list doesn't have to go in this order every time. It doesn't matter. I would suggest putting X's and Y's always the same just to keep it straight in your head. But your general steps would be to create this table, fill in what you know to begin with, determine what you're solving for, and any formulas you need, and solve it. Basic steps. So now on this slide, I've changed the question to be what I really want you to solve for, not the other one. So this same, we've got a bridge. It's 321 meters above a river. We kick the rock horizontally off a bridge. If the rock was kicked with an initial velocity of 5.6 meters per second, how far will the rock land from the bridge? So here's our table. It's our distance that the rock's going to travel down is going to be negative 321 meters. That is because the rock is going from bridge to ground, so it's going down, which makes it negative. Our initial velocity gives us a 5.6 meters per second. Since it's kicked horizontally, all of that velocity goes in the x. We're not breaking it down yet. Then your VIY is 0 because it's not kicked at any sort of angle to have any initial vertical velocity. We also know our accelerations of 0 and negative 9.8. Those are a given, right? So in order to find our sorry, lost my train of thought. Our distance, we need to know time. This formula that I have on the screen, it's for the vertical because that's what we're going to use first. We don't have enough information to find the horizontal distance immediately. We only have VIX and we only have acceleration, and all the formulas are not going to get us there. So this is where you're kind of going to hate me because you're going to have to do multiple formulas to get an answer. So in order to find time, most of the time, we're going to use the vertical information to solve for time. So we're going to use the distance formula, which is the formula you're also going to use most of the time, and plug in what you know. Since our VIY is 0 in this case, that cancels out, and we end up getting 65.51 equals t squared. Square root it, you get 8.09 seconds. So we had enough information in the vertical to solve for time. The same amount of time it takes this rock to fall to the ground is the same amount of time it takes it to go away from the bridge. All right, it's happening all at once. So the time is the same in both columns. So we can use that answer to then find a horizontal distance. So we would write into our chart 8.09 in both columns. So we take the same formula, but now in the horizontal. So I've got x's here instead. You plug in everything you know. Since our acceleration is 0, that part cancels out. So we're just multiplying 5.6 by 8.06, and that gives us 45.3 meters. So our answer to the question of how far the rock will land from the bridge is 45.3. This is similar to the lab you did in class with the marble rolling off the desk, and you're trying to predict where the marble will land. So you place the cup there. This is a similar kind of thing that you did there, all right? Just with less calculations because you're not having to measure stuff like you had to do in the lab. So that's type 1, right? Example 2 is a little bit longer. This is the second type of motion. We have got a cannonball fired from the ground at 100 meters per second at an angle of 30 degrees above the ground. So this cannon is angled up, shooting into the air at 30 degrees. We want to calculate several different things, and the first being figuring out our horizontal and vertical components. Anytime you have an angle, you're going to have to break that down using the last two formulas in the box on the formula sheet for this unit. We are also going to look at how long the cannonball's in the air for, how far it travels horizontally, and the maximum height that it's going to reach during its travels. All right. So for part A, you've already got the answers on the screen because I messed this up. We are going to use these two formulas that are on your formula sheet. VIX is equal to VI cosine theta. VIY is equal to VI sine theta. Those are both on your formula sheet. They're always the same. Please don't memorize them because you'll get to use your formula sheet on your test. Right? VIX is equal to 100 cosine 30. That gives you 86.6. VIY is 100 sine 30. That gives you 50. Right? You will not use this 100 meters per second again. I have had kids every year, they do this perfectly on the test, and then they get to part B, and they, for some reason, go back to using this 100, all right? These numbers are what you're going to use in your calculations, all right? So we're going to plug these into our chart. I've also filled in my accelerations that I know. All right, so for part B, we want to know how long the cannon's in the air. All right, so I'm going to use this formula, and this is typically what the same steps you're always going to do for these. When this projectile is launched into the air, when it gets to this highest point of its motion, it will have a velocity of 0. So if we just say, okay, that's where we're going to end this motion at, my final velocity is 0, I can plug in what I know, and I can get the time it takes to get there, which in this case is 5.1 seconds. Now in reality, my cannonball is going the complete parabola to the other side, so it's going to take twice the amount of time. It took it 5.1 seconds to get to the top and 5.1 seconds to get down. So in total time is 10.2 seconds. So majority of the time when you're solving these questions and you're looking for time for this type of projectile motion, you're going to use this process. You're going to solve for the time it takes to get halfway there and then double it. So at the top, your velocity is 0, which is why our final velocity is 0. Okay. Just like when we had the one-dimensional motion when throwing it into the air, at the very top, our final velocity was 0. It's the same thing here. At the very top, our final velocity is 0. Okay. So our full time here is 10.2. So I plug that into my chart. So now we want to know how far the cannonball is going to travel horizontally. So we're going to use our distance formula. You plug in what you know, which this one's easy. You just multiply in two numbers. You get 883.32 meters. And then the last one is to see what your maximum height the cannonball reaches is. So we're going to use our distance formula again, this time in the vertical. Now this is another common place people will mess up. We got the full time of 10.2 seconds. However, when you're reaching your maximum height, you are halfway through the motion. You are only taking 5.1 seconds to get there for this example. So we are going to use 5.1 in our calculations. We're not going to use the full time, all right? So when we use 5.1, because that's the amount of time it takes us to get to that highest point, after another 5.1 seconds, we're back to the ground, all right? So that's why you're using half. So when we plug everything in, we're getting an answer of 127.6 meters. So our object ends up traveling for a full 10.2 seconds. After 5.1 seconds, it's halfway to the top, which it's reached a height of 127.6 meters. And by the time it travels its full 10.2 seconds, it has gone a total of 883 meters, right? So that's everything I've got for you in these notes. Please let me know if you have any questions in class or in tutoring. I hope this video helps you out.